This will serve as an explanation of the vocabulary that we will use when we're dealing with exponential expressions. These are expressions because there are no equal signs. If there were equal signs and numbers on the other side, they would of course be equations. Each of these expressions has several parts, and we're going to go through them. We should be familiar with the word coefficient by now, and that is the number that occurs to the left of the variable. This x squared, there are one of those. So there's really an imaginary 1 here. The coefficient on this term is 1. Likewise, this term in the middle, the x by itself, is also one that has a coefficient of 1, and it also has an exponent of 1. The 6 is not a coefficient because there is no exponent next to it. If you wanted to get creative, you could say that this is really 6x to the 0 power, and if it were written that way, 6 would then be a coefficient, but because we're not looking at the variable, 6 is not a coefficient. It is known as a constant because no matter what value we choose to substitute in for x, this term will always equal 6. It will constantly be 6. So in this expression, we have 3 terms, x to the second power, x to the first power, and 6. 2 of these terms are variable terms, and each of those variable terms has a coefficient of 1. In this next expression, there are 2 terms, 3x and positive 10. 10 is a constant because no matter what value I substitute in for x, this term will always or constantly equal 10. This x is taken to the first power, and the coefficient of the first term is the 3, the number immediately to the left of the variable. In this next expression, we have only one term. Everything here is multiplied together. There's no addition or subtraction between these two, so this is one large term with a coefficient of 10. This x has an exponent of 2, the y has an exponent of 3, and this z has an exponent of 1. This expression has 2 terms. Again, the terms are separated by either addition or a subtraction sign. The 9 is a constant term. No matter what value we were to plug in or substitute for z, this term will always equal 9, constantly, so we call it a constant. This term, 8z to the 5th power, has an exponent to a power and a coefficient of 8. This expression has 4 terms. We are separated by addition or subtraction signs between terms. Here, the constant is negative 5. Let's include the signs with our constant, and we don't really refer to them except when they are negative. We could say that this is positive 9 and that this is positive 8z to the 5th, as long as we make sure to refer to the negative with the term. This term, 2x to the first power, has a coefficient of 2. Or positive 2 if you want to look at it that way. The sign goes with the term attached to it. This term, 7x to the third power, has a coefficient of positive 7. And this term, negative 3x to the fourth power, has an exponent of 4 and a coefficient of negative 3. When we're talking about different terms or expressions of terms, we can call them by their degree. And what the degree means is the highest exponent of any of the terms altogether. So here, the highest exponent of any of these terms is 2. So we would say that this is a second degree term, or polynomial. This is a first degree polynomial because the highest exponent is 1. When we have one giant term with multiple exponents, we have to look at the total of them. Note how this expression is separated into 3 terms because of the addition signs. This expression is one large term, so it is a 1, 2, 3, 4, 5, 6th degree term. This expression has only one exponent in it, and that exponent is to the 5th power, so this is a 5th degree polynomial. This expression here also has several terms. So when we're talking about the degree, we want to find the one with the highest exponent. And that would be this one, the 4. So this is a 4th degree polynomial.